Thank you, Piotr. It's a great pleasure to participate in this conference. I'm very sorry that I'm giving the talk remotely, and envious of you all sitting in the hallway, in the hall, that I can see a lot of people actually are there. So today, because it's a quantum optics conference, I figured that I will come in to start with a traditional quantum optics inspiration, and then move on to talk about what we can do with borrowed ideas from quantum optics on quantum matter, and you apply quantum matter for frequency metrology and optical atomic clocks and so on. So let me move on right away to tell you the story about suppression of atomic radiative decay. As we all know, atoms, once you're excited to the, it's one of those excited state, it wants to decay down by the coupling to the vacuum fluctuations, it wants to come down to the ground state, emitting a photon. If one can engineer such atomic natural lifetime, which appears to be one of the most fundamental properties of atom, one way to think about doing it is to change the atom's environment, which you can use this to modify its spontaneous emission decay. This would represent a quantum engineering of atomic natural lifetime. And we, of course, we know this is possible, and this field has existed for a long time, starting back in the 1940s, even as early as 1940s, when Purcell first discussed the change of the boundary conditions of where the atom sees. And if it can squeeze out the modes for the photon to decay, you can actually block the photon modes, the so-called vacuum modes, and use that to prolong the spontaneous emission lifetime of excited state of atom. And this basic idea is giving rise to this vibrant field of the cavity QED. It's really one of the cornerstones of quantum optics of modern times. But oftentimes we talk about this photon sector, try to block the electromagnetic modes of the vacuum to make the atom lifetime to be longer, the excited state lifetime to be longer. Equally, on the equal footing, then one can think about there is a motional state of the atom. When the atom gets excited and emit a photon, it's going to go to a particular momentum state because there's a recoil of the photons. What if that you make a degenerate Fermi C, where all the motional states around this excited atom has been occupied by other identical fermions? Therefore, from the matter point, from the sector of the atomic point of view, the motional states is actually blocked, just like the photon itself is being blocked, such that an excited atom cannot decay. Is that possible? This idea has been thought about very early on, even before the demonstration of the Fermi degenerate gas. The basic idea is, again, Pauli blocking, where if you imagine you have a T equals to 0 Fermi gas, all quantum mechanical motional states are occupied. And suppose you have one excited atom embedded in the T equals to 0 Fermi C. And if the photon recoil energy associated with emitting or absorbing a photon is smaller than the Fermi energy of that Fermi C, this atom simply cannot decay. And this idea was predicted over 30 years ago, as I mentioned, at the beginning of the 1990s, 10 years before the production of the Fermi degenerate gas by Debbie Jing. But yet this effect was never really truly observed until today. So I'm going to tell you a little bit of a story about how we observe this. It's actually easier to understand in the momentum space. This circle represents the so-called Fermi momentum, which is associated with the Fermi energy. H bar kf squared over 2m is the Fermi energy. A photon comes from the left, and you excited atom from ground to excited state. There's the absorption. There's a photon recoil associated with that absorption of that photon. And then the atom will get to the excited state and re-emit the photon. And suppose you detect a photon at this particular angle, d alpha, and associated with that emission, there's a photon recoil, and it's represented by the arrow of the K emission. Putting this together, absorption recoil and emission recoil, there's a net momentum exchange of K induced by these two photon process, absorption and emission. And this K, of course, is bounded to be less than at a maximum 2 photon recoil momentum. right? It's all of that is easy to understand. Now, the suppression is such that if this k vector, that the momentum, the net momentum change of the atom is within the Fermi momentum space, well, there's a suppression of this process. The suppression is given by this particular structure factor, which is nothing but counting for all available final momentum states there, the hole especially, where the atom can actually decay into, and then average over all the initial momentum states within the Fermi sea. And that will give rise, a very simple expression will give rise to the so-called suppression of the spontaneous emission decay. Now, of course, there are limits to the blockade effect. There are so-called edge effects. Now, suppose that if the atom is living by at the surface of the Fermi sea, then of course it can recoil out of the Fermi sea, and then in free space, there are no other momentum states being blocked by other atoms, and so the atom, this particular atom, can freely decay. But if those atoms are embedded in the middle of the Fermi sea, it's much harder to decay. So there's surface to volume ratio. You want to make a big Fermi sea to observe this effect. Another limit is the finite temperature. We can't really make a T equals to 0 Fermi sea, and there will be at this finite temperature, there will be a thermal de Broglie thermal wavelengths coming in to MKBT, and then make the Fermi sea filled up with holes. These holes can take up the momentum, recoil momentum of the excited atom, such that the spontaneous emission becomes possible again. And so at finite temperatures, the suppression factor will be weakened. Now we do this experiment in the so-called light scattering configuration. This is actually nearly two-dimensional Fermi degenerate gas in the middle of the beam here that is a blue probe, and I'm going to explain what blue means. It's a probing a particular transition strontium atoms from single S0 to single P1. This happens to be at a wavelength of 461 nanometer. We actually performed the experiment in very small scattering where the probe time is actually much longer than lifetime. So we are measuring something in steady state and looking at the reduced photon being scattered by these atoms, because you have put these atoms into deeply degenerate Fermi degeneracy. And we also maintain a fairly weak excitation, meaning each atom is scattering far fewer than 1 photons. This is to preserve the ground state Fermi sea. And we do that by detuning from the atomic resonance by about 40 line widths away. And you can see that we have two different cameras. One camera is observing angle that's a fairly small with respect to the original incident light beam, K vectors. The other one is nearly orthogonal to the original incident beam. And I can explain to you the reason behind this, making these two configurations. For the momentum that's for the direction of camera 1, the recoil momentum, as you can tell from the upper left cartoon, you can see the emission momentum is of course going from top down, because we are scattering a photon into the camera 1. So together with absorption photon and the scatter photon and re-emitted photon, because of the small angle subtended between these two directions, the net momentum exchange K is rather small. On the other hand, for the camera, which is almost perpendicular to the original incident direction of the photon, 72 degrees to be exact, we can see there's absorption photon recoil and there's emission photon recoil from the camera 2's direction moving backwards. And the net momentum exchange factor K can actually in fact be bigger than the Fermi momentum space. And so we expect that the direction along the 24 degrees in camera 1, you will see a reduced scattering, while in camera number 2, you will see almost no change of the photon scattering rate. The challenge doing those experiments is you are dealing with a very high atomic density, and the density can exceed 10 to the 14 atoms per centimeter cube. So there's lots of collective effects, such as superradiance, and it's almost very difficult to suppress it. Multiple scattering, radiation trapping, all of these effects can play a role, and you really have to be very careful with those systematics. And one of the fact that we use actually the tuning here is to circumvent one of the key issues of a multiple scattering of the photons. And indeed, this is true. If you take a picture of this, that were Fermi degenerate gas, actually this picture is taken by filling the Fermi gas in a three-dimensional optical lattice. And you can see the filling factor per unit cell is nearly 85%. So it's very highly filled. The density is exceedingly high. And if we take a picture of these Fermi gas, you can see that it does not represent actual atomic distribution when you try to probe on resonance. That's because optical density oftentimes can exceed 100. So in this tremendously dark crowd, in fact, there's a lot of multiple scattering, a lot of collective radiative dipole coupling effects. And a much better picture is to use huge amount of intensity, really well above saturation, and just to bleach the whole atomic crowd. You can do so-called high intensity imaging, use fluorescence, or you can use far detuned absorption beams. In our case, 40 line was detuned away, as I mentioned earlier, and they take a much more faithful picture of the atomic distribution of the Fermi gas. There's also a suppression geometry to discuss. As I mentioned earlier, we have these two different angles to observe the suppression versus no suppression. In the case of when the Fermi energy is 10 times the recoil energy, nearly the entire sphere shows a suppression for the photon rescattering. The little blue arrow indicates the original photon propagation towards the upper direction. So the color indicates the suppression factor, the darker meaning the bigger suppression. Now, if you lower the Fermi energy to be only about 1 recoil energy of the photon recoil, then the suppression actually in the backwards is no longer suppressed, because in the backwards scattering, the momentum exchange is actually very small, as I showed earlier, and therefore the suppression factor, in the direction of the backwards direction, the photon recoil, the momentum exchange is actually much bigger. The photon recoil, twice the photon recoil nearly, and that's much bigger than the Fermi momentum space. Therefore, it's no longer suppressed in the backwards. Only in the forward direction, in a small cone, you will see suppression, because there the momentum exchange is still much smaller than the Fermi momentum of the gas. So you should be able to expect to see a distribution of the suppression factors according to which angle you're observing the scattering. And this is exactly what we see. So now there are two curves here. One is a red curve obtained by the camera, which is 72 degrees away from the forward direction. The other one is only 24 degrees. So this forward direction, you see a much bigger suppression factors. In this particular case, we kept the Fermi energy over the recoil energy to be about 1. So this indicates the case EF over ER equals to 1 in this cartoon picture that I showed earlier. And we just continue to lower the temperature of the gas. And as you can see, the bottom axis, horizontal axis, represents T over TF. As you go from 0.7 going to 0.1, much deeper into the quantum degeneracy, we achieve a suppression factor of nearly 50% at deep quantum degeneracy. Similar experiment can be done by actually keeping T over TF to be a constant at a 0.13. So take this point, and then you gradually weaken the optical trap, where the Fermi energy, what you're plotting now in the bottom axis is a ratio of the Fermi energy of the recoil energy, or the momentum of the Fermi over the recoil momentum, Kr. R represents the recoil, F represents the Fermi. And as you can see, the trap gets weakened, and the suppression factor gets smaller, and the suppression factor gets less pronounced. But still, nevertheless, even at a 0.7 Kf over Kr, as long as the T over Tf is still deep in the quantum degeneracy, you still see a fairly large suppression factor by 30% also, compared to the case when you're looking at a perpendicular direction where there's basically no suppression factors. We can also look at the entire Fermi sea. Remember I mentioned earlier, there's an edge effect. Towards the edge of the Fermi sea, you're expecting to see much smaller suppression compared to the center of the Fermi sea, where the suppression factor should be largely concentrated. And so again, using the Fermi gas of a 0.1 TLTF, you see a much larger polyblocking near the center of the image. Is there a question? No. And we took the image by azimuthally average the spatially resolved photon counts from the Fermi crowd. I'm telling you this, this kind of the motivation. I want to connect this to what we have been working on, on the quantum metrology of building better atomic clocks. So here is actually the structure of the strontium atoms. We all know strontium has 2 valence electrons that forms the spin singlet and spin triplet. The transition we've been working on the Fermi suppression is a singlet S0 to singlet P1. This is a strong transition. But we also know there's so-called a spin forbidden transition, the intercombination line from singlet S0 to triple P1 at 689. We can do narrow line cooling, or the actual clock transition that going from singlet S0 to triple P0. The clock transition lifetime is 120 seconds. 20 years ago, when we started working on this strontium atom as a quantum, as a clock, we thought this 120 seconds, that's a long time away from us for us to achieve that. But as I will show you in the remaining time about the advancing in quantum coherence, we are now getting very close to demonstrating this lifetime limited quantum coherence at 120 seconds. So you can see that that's where the motivation of engineering spontaneous decay and so on is coming from. So, well, the first thing we can actually be thinking about is, can we make the lifetime from triple P1, which is about 22 microseconds, represents the lifetime, represents a line width of 7.4 kilohertz. Can we make this lifetime 21 point something microsecond longer than the natural lifetime of triple P1? And it turns out the strontium atom, the fermionic strontium atom, has actually 10 nuclear spin states. And let's focus on just 2 of them. MF equals 9.5 and 7.5. The nuclear spin is 9.5. So you have 10 nuclear spin states in the ground. If you prepare 2 Fermi Cs, there's a collapse-Golden coefficient that one is 0.18 from 9.5 to 9.5. And then from 9.5 to 7.5, the collapse-Golden coefficient is 0.82. So if you prepare 2 Fermi Cs in the ground, and then you drive the minority component, you make the MF equals 9.5 Fermi C to be much smaller, 10 times smaller than the Fermi C at MF equals to 7.5. And you drive this minority Fermi C component to the excited state. Then the atom wants to decay. But most of the atom would like to decay according to the collapse-Golden coefficient down to the MF equals to 7.5, because the ratio of collapse-Golden coefficient is more than factor of 4. However, if you have a majority of Fermi C locating and occupying MF equals to 7.5, you will actually block this 0.82 collapse-Golden coefficient, forcing the atoms to decay back down to the MF equals to 9.5. So you can look at the blockade effect by actually simply looking at the lifetime of the triple P1 will be extended, and the ground state spin distribution would be different. Will be different from what collapse-Golden coefficient would tell you. Rather, it would actually all come down to the 9.5 instead of optically pumped into the MF 7.5. Again, the geometry matters. You have to avoid superradiance, multiple scattering. So if you do experiments like this, if you make a Fermi C and you probe this along the direction where the optically thick axis is lying around, this effect will be masked tremendously by superradiance and multiple scattering. But the best geometry is actually prepare Fermi gas in a 2D geometry, and you probe it along the thin axis of the OD. And doing so, you can avoid to much large scale of the entire superradiance effects. There's still some multiple scattering within the pancake, but the effect is much reduced, and you can actually start to observe some of the signatures of the polyblocking of the spontaneous decay in the triple P1 sector. And some of the evidence is presented in this paper on the archive. This, you may be asking, like, how do you prepare these different Fermi seas? It turns out the strontium has this interesting property, that's so-called SU symmetry, where you have two electronic state, and here now I'm talking about clock state, single S0, triple P0, and then inside each electronic state, where you have total electronic angular momentum J equals to 0, but you have a nuclear spin of 9.5, therefore there's 10 nuclear spin states. But I dot J term equals to 0. There's no hyperfine couplings. Therefore, you can have different nuclear spin states, but they do not really influence how the atoms come together, electronically interact, except the influence by the Fermi statistics. So this I dot J term gives rise to different spin states interact in the same way. This is what SUN symmetry is about. And so if you prepare the entire gas with 10 different Fermi seas, you can cool them down very effectively. And this is neither the case of the pure bosons, where you have a Bose-Einstein condensate where all the atoms come down to the absolute ground state, versus in a single component fermions, these atoms occupy different motional states one by one due to the Pauli exclusion principle. If you have 10 different nuclear spin states, you will still be, each one of them is still a Fermi C, but within each motional state, you can have 10 atoms with different nuclear spins occupying, because distinguishable fermions do not obey Pauli exclusion principle. And therefore, it's in a very interesting regime where it's a Fermi degenerate gas. At the same time, you have a very strong interactions due to the fact that these different nuclear spins can interact with each other. And the practical consequence that we enjoy is that we can take 10 spin states or evaporative cooling them simultaneously, and we can produce a very deeply degenerate Fermi gas in a short time. Actually, in like half a second evaporative cooling, we can produce 10 Fermi Cs with T over TF of 0.07. And this then we can use optical stock shifts, sort of an optical Stern-Gallagher kind of experiment to select a single nuclear spins. Maybe this it's a particular moment of, excuse me, my office light has automatic turn on, turn off. Let me just turn this on really quickly. My apologies, I'm back, but it's actually a good little break because I want to tell you why we are so interested about engineering, quantum state engineering of the coherence of the lifetime. We are already, if you want to build the next generation quantum sensors or atomic clocks as example here, we want to have a long coherence time. We want to have possibly starting to engineer the quantum interactions such that we can achieve well beyond the standard quantum limit, which is limited by the number of particles taken to the power of the half. And we want to protect, of course, by putting lots of atoms in the quantum system, we want to protect the quantum coherence and really enjoy the enhancement that we can using the interaction to engineer entanglement and so on. So this has been sort of the conference of the two frontiers, one from quantum science, one from precision measurement frontiers, from state preparation now to system engineering, from maintaining increased quantum coherence to eventually being able to use the entanglement, as we heard from previous talk, when we start to look at entanglement of macroscopic samples of atoms. So that's the basic motivation. And indeed, as you can see, the reason why we have been working on this deeply degenerate Fermi gas is we want to make a quantum mod insulator or Fermi insulator clock of a three-dimensional space where each atom occupies one particular optical site. And in doing so, if we can load 1 million atoms in there and enjoy this very long quantum coherence time, say 160 seconds, 120 seconds of the lifetime of these atoms, then you can achieve a clock with a precision of few + 10⁻20. And this is factor of 1,000 improved over the previous record. And as I mentioned, our previous record, because that's a published record of a 3 times 10⁻17 at 1 second. And in fact, the progress I'm sharing today, we have now already achieved better than this number by factor of 10. So this large motivation of being able to quantum state engineering of a large number of atoms and protecting this quantum coherence really directly lies within our motivation of building, pushing the frontiers of quantum sensors and optical atomic clocks. So by loading these degenerate Fermi gas into the 3-dimensional optical lattice, we can guarantee every atom is confined in the lowest motional state. And therefore, you can actually see a very clean set of the carrier transitions and so-called motional side, upper motional sidebands and lower motional sidebands disappeared because atoms are all occupying the lowest possible motional states. If you put it, like I mentioned earlier, 10 different nuclear spin states into the quantum system, then of course the Pauli exclusion principle does not apply to these distinguishable fermions, but these atoms will interact and create the so-called sidebands, not influencing the actual carrier transitions where you only have 1 atom per site. And these sidebands are occupied by Fermi symmetry and anti-symmetrization between these 2 wave functions, because those are fermions and you have to anti-symmetrize either through symmetrized electronic degrees of freedom, anti-symmetrized nuclear spin, or vice versa, anti-symmetrized electronic degrees of freedom and symmetrized nuclear spin degrees of freedom. And those are the sidebands which are away from the optical carrier that you can use for building a clock transition. And these are a few years ago, we achieved a very long coherence time. At the time, 6 seconds was a record. And in recent years, we've been pushed towards 12 seconds. And we used this particular technique to do some imaging spectroscopy, where this 3-dimensional optical lattice we put on a very high resolution, spatial resolution microscope lens in front of it. And then as we drive the clock transition, and if we apply, for example, a magnetic field gradient, you can actually image the optical frequency being shifted by a small magnetic field gradient. And you can image 1 atom, a few atoms at a time. And it really is starting to give us the sense of, well, I can measure the frequency difference with such high precision. In a few hours, I can measure the frequency difference down to a few + 10⁻19. Maybe this gives rise to the hope that we can really pushing towards extreme space-time resolution, where this optical lattice is sitting, of course, on the surface of the Earth. And if you can measure the time at the level of 10⁻21, then you can really start to see the time from different layers of optical lattice start to evolve with different time because of the curved space-time. Motivated by this, we actually did a very recent experiment. Instead of in 3D lattice, we actually went back to a 1-dimensional lattice, but making the lattice exceedingly homogeneous and very large pancakes to reduce atomic interactions. And in this particular configuration, we made a very, very big lattice such that the vertical extent is covering 1 millimeter distance along the direction of the gravity G. And in fact, the atoms are cooled down to about 100 nanokelvins or so. And between each individual pancakes, there's a gravitational potential shift, which is given by nothing by the G times λ/2. So there is an energy difference by about 850 hertz between individual pancakes. And we can actually see this is actually experimental data, the so-called Stokhovonius states. The black one is the transition of the optical carrier, and the blue and the red sidebands are actually measuring the wave function overlap between 1 center site to a number of sites displaced either vertically up or vertically down. And if you zoom into the optical carrier transitions, it enjoys a very long coherence time. In fact, as the coherence time can be measured by so-called correlation spectroscopy, we take an image of the upper half versus the lower half and just measure the population correlation between the upper half's excitation fraction P2, we call it, and the lower half's excitation fraction P1. And if you wait, this is basically a Ramsey fringe contrast. If you wait 20 seconds, you can see there's a frequency evolution due to the magnetic field, and there's a phase opening up, but you can still see a very big contrast. If you waited 50 seconds, the contrast is still very finite. And if you plot all of this together, the contrast of the Ramsey fringe is now almost 1 minute long. This is by far the longest quantum coherence that people have observed in spectroscopy, representing a quantity factor of 5.6 times 10 to the 6th for thousands of atoms here. Using this, we can actually, using a microscope image, to measure the frequency distribution of an entire cloud. And this is the gravity pointing from left to right. This is the cloud actually located in the vertical direction for about 1 millimeter. And you can see we can measure the frequency, fractional frequency shift across the entire cloud in the unit of 10 to the minus 19 scale as a function of the displacement in the vertical direction z. And if you plot these measurements together, these are measurements spanning over 15 days, 2 weeks. You can see there's a red line predict gravitational redshift of 1 times 10 to the minus 19 minus 1 times 10 to the minus 19 for 1 millimeter difference in the vertical direction. And our experimental data essentially completely agrees within its error bar of this predicted gravitational redshift over 1 millimeter. And my final slide really shows that this very exciting new measurement capabilities with this long coherence time, where now we can reach 1 times 10 to the minus 20 in 10 to the 5 seconds. In fact, for over the entire measurement time, we have made 3 times 10 to the 5 seconds, just a little over a day. We reached in each half of the clock 6 times 10 to the minus 21 for each clock. So clock measurement precision is now entering 21 digit, and we can easily resolve this 1 millimeter gravitational redshift within a single atomic ensemble. So this is really trying to make the connection of why the quantum coherence plays such an important role for pushing the frontiers of quantum metrology. With that, I want to thank the graduate students, especially Toby, Colin, and Alex, who have been pushing on the Strontium 1 experiment, and a collection of students and postdocs been working on the three-dimensional optical lattice clock, along with the stable lasers by Drew, and long-term collaborations with Anna Maria Ray on theory, and as many collaborators as well worldwide on these Strontium clock project. Thank you very much for your attention.
Thanks a lot, Jun, for this amazing talk. So at this time, we would like to invite any questions.
You, and sorry for taking it a little over your 30-minute limit.
Hi, Jun. Jun, on your Fermi tenfold band insulator interaction spectroscopy, there was a little sideband above approximately 100 hertz, I think, if I saw that correctly, to the red, that you did not mark. What? Yeah, this one, this very small thing there, near the carrier. Is that some signal or?
No, I think to be honest with you, this was never reproduced, and it later just wasn't there. So we believe probably as we were scanning at that particular day, the laser had some jitter or something. It wasn't. Actually, you actually raised a really good question. I'm not sure if I have a slide for it. But if I do, it will be interesting to show you, because it's actually to convince you, or we actually looked into that possibility if there are other spin state. Oh yeah, this slide. Now, for example, instead of having just 2 atoms, you could imagine you can occupy, and this is not showing. You can see it, right? You can still see this. I'm sharing the slides. And you can see, this n equals to 1 is a 1 single atom occupied. 2 is when you have 2 atoms occupied, either in the spin symmetry nuclear spin anti-symmetrized or nuclear spin anti-symmetrized case. And now you can see the 3 spins, 4 spins, 5 spins, 5 different atoms with different nuclear spins in there, and we can resolve them all. And that little sideband you observed was never part of this multiple spin components. So therefore, I think that the very first thing, you're being very perceptive, and that signal that we saw is not because we had a 3 spin in there or 4 spin in there that had a little bump in the left-hand side of the red spectrum here. This one, yeah. So hopefully you were able to see when I showed you with 3 spin, 4 spin, 5 spins, and you can see that the energy resolution is high enough that you can resolve all these interaction sidebands by multiple spins.
Okay, thanks.
Do we have any other question? I don't see any question.
I have a question.
Participants.
So you showed quantum systems with high coherence times, in fact, record coherence times. But can you actually implement quantum gates on these systems? Can you rotate those qubits or something like that?
The question is about whether we can implement quantum gates. Is that what you're asking?
Yes.
Yes. Excellent question. And I don't know if I have a slide here. I may not. We have in the 3-dimensional optical lattice, in order to, okay, I don't have a slide. I don't need to waste time on that. Let me just answer your question. In this particular system, it's difficult to implement quantum gates just because we do not have enough optical resolution to see each individual site. Our optical resolution is about 1 micron, and the side-to-side distance is 400 something nanometers, and 813 divided by 2, so 4 or 6. And so we do not have the capability to resolve individual site. Although one could, with such high spectroscopy resolution, what you can do is actually to apply, for example, magnetic field gradient, and you can actually select individual atoms. But the people have, of course, can make accordion lattice, and there are now also experimental groups like Adam Kaufman's group in Jela have implemented using strontium atoms, implemented optical tweezer, where you can make the atom-atom distance to be a few microns apart, 4 microns apart. And of course, interaction becomes much weaker unless you do Rydberg atom physics experiments where using dipolar interaction to implement gates. So there are experiment effort in both Caltech, Jela, and other places where you can use strontium atoms to start to implement quantum gates. So quantum information protocol and the clock experiment start to merge together, but not quite in the traditional optical lattice experiment, just because the spacing of these lattices is so tight.
Okay, so and when we sort of change the spacing between the atoms so that the gates can be implemented, or apply a magnetic field gradient so that the magnetic field sees individual atoms, does this affect the coherence time? Because the coherence time seems to be the main attraction of your system.
So the magnetic field you want to be able to control. In fact, in our experiment, we do control the magnetic field extremely well, just because these atoms can actually sample the field fluctuations with a very high sensitivity, even though those are nuclear spins. But because the coherence time is so long, we can actually measure the magnetic field. So yes, the idea of being able to control the magnetic field and use this to select individual atoms is definitely a direction. You can also address so-called cluster state generation, which you can do spectroscopy in a macroscopic version. Instead of doing individual atom and do gates based on individual microscopic control of individual atoms, you can address them in a cluster, and then use the cluster state generation to process quantum information. That's another research direction that's possible, where you do not require individual atom measurement, but rather just do macroscopic spectroscopy measurement, such as Ramsey fringe and spin echoes and so on.
Thanks.
Great, thank you. I think that Although there are some other questions, we run out of the time for this part. So thank you, Jun, very much.
Thank you.